Electrostatic potential energy. You know that electrostatic force is a conservative force, and conservative force, when we do some work against conservative force, then that work conserved as potential energy inside the system. Now we are considering a charge Q. The charge Q is fixed at this point. We will take this point as a reference point, and another charge small q is at this point. So this is P point. This is O, origin. Now for simplicity, we are taking both Q and capital Q and small q are positive. We can say that electrostatic force will act in this direction. Suppose this is Fe, electrostatic force. Now we are selecting another point R, and constant force, external force, is applied to move charge Q from P to R. In that case, the force, that is the force which we apply on the body, should be opposite to, this is the external force, should be opposite to the Fe, and F external should be equal to electrostatic force in opposite. That means their magnitude are same and direction is opposite. Why magnitude same? So that there will be no acceleration of the object, and we are moving charge small q with a very negligible speed, so that the kinetic energy due to that speed will not change the result of the system. Now the work that the external force can do is equal to F external into the distance covered by it. Say this is very small, so R. Suppose this is position of this R suffix R, and this is R suffix P. Now we are considering another point which is at a distance R and which is in between these two at any point. This is at distance R, and for a very small displacement dr, the work to be done dw is equal to F external into dr. We are exerting force in this direction, body is displaced in this direction, so in this case work is doing by the force. But if we convert it into the electric force, then that will be Fe here as it is, and Fe is equal to q by 4 pi epsilon 0 r square. So W is equal to minus q by 4 pi epsilon 0, this is a constant part, and 1 by r square dr, and initial position, that is Rp to Rq, R, that is equal to minus q by 4 pi epsilon 0 into 1 by R minus Rp to Rr is equal to q by 4 pi epsilon 0, and this minus will be cancelled with this minus, so 1 by R suffix R minus 1 by R suffix P. Now we know that work done by the external force is stored as a potential energy, so we can say that potential energy U is equal to W external is equal to, this is W external, that is equal to q by 4 pi epsilon 0 1 by R minus 1 by Rp. Now what will be the potential energy? This is the potential energy, potential difference. This is potential difference, that means del U, that means U R minus U P is equal to Q P by 4 pi epsilon 0 1 by R R minus 1 by R P. Suppose now we want to find the potential energy at R. Now, how is it possible? We are considering that when this positive charge Q is at infinite, then potential energy stored at that point infinite is 0, because force becomes 0. At infinite, force becomes 0. So when T tends to infinite, UP is equal to 0. Therefore, UR, that is potential energy at some point, UP, P tends to infinite, that means RP tends to infinite. So putting this, we can find epsilon 0 1 by R. Therefore, from this we can say that potential energy at a point is equal to Q by QP by Q, small q, not QP, small q, 4 pi epsilon 0 to R. Now, this is potential energy. Now, potential at a point. Potential at a point when a negligible charge, that is test charge, bring from infinite to R distance. That means when Q tends to 0, U by Q, that is equal to V. Okay? Or we can say that limit Q tends to 0, U by Q, that is equal to V. So simply if we divide this, then we will get potential at point V is equal to Q by 4 pi epsilon 0 to R. Now, it can be derived from another way, that is from the electric field. We know that electric field E is equal to Q by 4 pi epsilon 0 R, and the whole derivation, when we divide a phi by Q, then this become, suppose limit Q tends to 0, if E by Q is equal to E is equal to Q by 4 pi epsilon 0 R square. Now, what will be the expression for external work? W is equal to WEXT is equal to minus Q by 4 pi epsilon 0, and that will be Q by into 1 by R square dr. So in this case, V is equal to del V is equal to minus E dot dr. Del V dV is equal to minus E dot dr, because when we divide W divided by small q, then this become dV dW divided by Q is equal to dV, and this is external, that is equal to du by Q. Okay, therefore we can find VR minus VP is equal to integration minus E into dr from P to R, that is RP to RR is equal to minus integration RP to RR Q by 4 pi epsilon 0 R square dr, and the result will be VR minus VP will be Q by 4 pi epsilon 0 into 1 by R minus 1 by RP. Therefore, potential at a point is equal to Q by 4 pi epsilon 0 into R. Now, potential due to system of charges. Suppose there are different charges at the space and we want to find potential at point P due to all these charges. Now, this is Q1 and position R1, Q2 and position R2, Q3 and its position R3. Now potential due to Q1 is equal to Q1 by 4 pi epsilon 0 R1. Next for Q2, Q2 by 4 pi epsilon 0 R2 and R3 and so on. So net potential V is equal to 1 by 4 pi epsilon 0, that is common part, into Q sigma Qy by Ri. We know that P and U, that is potential energy and potential, both are scalar quantity. So we can say that just algebraic summation is sufficient to find the resultant potential due to several charges at the space at a given point. Okay. Now equipotential surface. Suppose this is a point charge, and if we draw a sphere around it of radius r, now at every point on this sphere potential will be q by, suppose this is q by 4 pi epsilon 0 r. Therefore potential difference between 2 points on the sphere is 0. As there is no potential difference, if we want to move any charge on this spherical surface, we need not to do any work. That is, this surface is called equipotential surface. Now we know that dV is equal to minus E dot dr. So dV is a scalar quantity and this is dot product is equal to minus E dr cos theta. We know that the value of E is non-zero, as there is a charge at the center. E is non-zero, R also non-zero. Equipotential, that is potential difference between 2 points on this sphere, is 0. So 0 is equal to minus E dr cos theta on the surface. So it is clear from the expression that this 0 comes due to cos theta. Cos theta is equal to 0. That implies theta is equal to pi by 2. It is clear from this expression that electric field is normal to the equipotential surface. So this is radially outward direction of the electric field. Now characteristics of the equipotential surface. Two equipotential surfaces never intersect each other. Suppose this is an equipotential surface, another, this is equipotential surface. Suppose they intersect each other at some certain point, then direction of the electric field normal to this, so it will be in this direction, and normal to this, so this will be in this direction. And it is not possible to get electric field in two directions at a certain point, because we know that if we keep up test charge at any point, it will move in a certain distance, and that distance signifies the direction of the electric field. So at every point we will get a unique direction of the electric field. So this is not possible to get two different directions of the electric field. So we can say that two equipotential surfaces never intersect each other. Next, we can draw equipotential surface. Suppose by this way. Suppose there is a field pattern like this. So every point we have to draw a perfect normal. Suppose this and this normal direction. This another point, the normal direction. This is the normal direction. So that may be the equipotential surface due to this field distribution. By this way we can draw equipotential surface. Now the potential energy stored in a system of charges. Suppose a charge Q1 is fixed at this position, as there is no field around it, so it has no potential energy. Another charge, say Q1, Q2, another charge Q2. Now we want to place another charge Q2 at a distance R12, the potential energy stored will be equal to the work to be done to bring this charge Q2 from infinite to this distance R1, and that will be equal to 1 by 4 pi epsilon 0 Q1 Q2 by R12. Now third charge Q3 is at a distance from Q1 Q13 R13, and from R2 this is R23. So energy required to bring this charge from infinite to this point will be equal to Q1 Q2 Q3 divided by R13 into 1 by 4 pi epsilon 0 plus Q2 Q3 by 4 pi epsilon 0 R23. Therefore, total energy stored in this system will be equal to sum of these three, and so on. If you want to increase the number of charges, that will be increased in this way. So we can say that total energy stored, potential energy stored, is equal to 1 by 4 pi epsilon 0 into Q1 Q2 by R1 R12 plus Q2 Q3 by R23 plus Q3 Q1 by R13. Now another thing, suppose there is a field at this position, it exists at this position, and at a certain point will be E, and its potential at this point is V. Therefore, the energy stored, if you want to bring up charge from infinite to this point, that's Q1 at this point, will be equal to V into Q, V into Q1. Suppose this is V1, say. Now we are selecting another point which is at a distance R12, and this is Q2, and at this point potential is V2. Work to be done to bring this charge from infinite to this point is equal to Q2 into V2 plus Q1 Q2 by 4 pi epsilon 0 into R12. Therefore, we can say that total charge of total energy of the system will be this plus this. Now, if we bring third charge Q3 at a distance R23 from Q2 and R13 from charge 1. Therefore, the total work to be done is equal to potential at this point is V3. Therefore, total work to be done Q3 into V3 plus Q3 into Q2, that Q1 by R31 into 4 pi epsilon 0 plus Q3 Q2 divided by R32 4 pi epsilon 0. So total potential energy stored in the system will be V1 Q1 plus V2 Q2 plus V3 Q3 plus this Q3 Q1 Q2 by 4 pi epsilon 0 R12 plus Q2 Q3 4 pi epsilon 0 R123 Q1 Q3 by 4 pi epsilon 0 R13. This will be the total energy stored in the system. Now, energy stored in a dipole. In case of dipole, you know, this is minus Q and this plus Q. They are at a distance twice L. So, we can say that the energy stored inside the dipole is equal to minus U is equal to minus Q square by 4 pi epsilon 0 into twice L. This is the energy stored in the dipole. Now, we want to find the potential at certain point due to this dipole. Suppose this is minus Q and plus Q. We are taking the middle point of the dipole as the origin, the point of reference O, and we are selecting a point which is far away from the center of the dipole. Length of the dipole is twice L, and it is at a distance r and at an angle theta. Now we can say that the position vector of this dipole will be, or its coordinate, r cos theta in I direction and r sin theta in j direction. This is a position vector with respect to the origin, and position vector of this is equal to Li, and this is minus Li. Therefore, the distance between these two, suppose this is A, this is O, and this is P, and P be the point. Now, AP is equal to this r cos theta minus Li, that is plus L, to I plus r sin theta j. Therefore, magnitude, this is vector, and magnitude of this AP is equal to root over it is r cos theta plus L whole square plus r sin theta whole square. Therefore, AP is equal to root over this, AP is equal to root over L square plus r square plus 2Lr cos theta. Similarly, BP is equal to root over L square plus r square minus 2Lr cos theta. Okay, that can be written as, if we take r common from the whole, that will be r root over L by r whole square plus 1 plus 2 L by r cos theta is equal to r. Since L by r is very small, we can ignore it. So 1 plus twice L by r cos theta. On the other hand, BP can be written as root over 1 minus 2L by r cos theta. Now, potential at point P due to plus Q charge is equal to VBP is equal to plus Q divided by 4 pi epsilon 0 into BP is equal to Q by 4 pi epsilon 0. BP is equal to root over 1 minus 2L by r cos theta is equal to Q by 4 pi epsilon 0 into 1 minus 2L by r cos theta 4 to the power minus half. By binomial expansion of this, we can write it as VBP is equal to Q by 4 pi epsilon 0, and there is r into r, and this is, by binomial expansion of this, we can write it as 1 plus L by r cos theta, and VAP is equal to, this is minus Q 4 pi epsilon 0 r into 1 minus L by r cos theta. So, net potential at this point V is equal to, V at P is equal to Q by 4 pi epsilon 0 r 1 plus L by r cos theta minus 1 plus L by r cos theta, that is equal to 2QL cos theta divided by 4 pi epsilon 0 r square. And we know that 2QL is equal to P, that is dipole moment, cos theta divided by 4 pi epsilon 0 r square. So, BP can be written as P dot r cap divided by 4 pi epsilon 0 r square. Now, potential energy stored inside a dipole due to external electric field. Suppose the dipole and direction of the field is along this direction, E, and it makes an angle theta, the middle point of the dipole. This makes an angle theta with the direction of the field. We know that direction of the, if it is negative and this is positive, and length of the dipole is twice L as usual. Therefore, we can say that torque is equal to P cross E, that is PE sin theta, magnitude of the torque is equal to, and direction will be normal to P and E. Now, work done W is equal to T into theta from theta 1 to theta 2. That is the work done due to the torque is equal to theta 1, theta 2 is equal to PE sin theta is equal to PE d theta, that is minus cos theta, theta 1 to theta 2 is equal to PE to cos theta 2 minus theta 1. Now, work done by the electric field is equal to this. Therefore, potential energy stored is equal to minus W, because work done by the, we know that W electric is equal to minus U, and W external is equal to U. This is internal, that is electric work done due to electric field, that is equal to minus W is equal to P into E cos theta 1 minus cos theta 2. This is the potential energy stored in the dipole under electric field.